I'm going to do a quick example of Lenz's law in action. This is a little more focusing on when the magnetic flux density changes with time. So my example is you've generated a magnetic field, magnetic flux density B, and it's coming from a solenoid or something, some source where you can turn a knob and you can change its magnitude. And suppose you've got a metal ring, something that can carry a current surrounding this magnetic field. So here we've got B, and it's got some flux going through this metal ring. And suddenly, we're turning this knob on this solenoid. What I'm talking about is maybe there's some big coil surrounding this whole thing. And you're turning a knob and changing the amount of current flowing through it. And you turn that current down. B is going to get a little smaller. Really attack that thing. Turn it down. And if you turn that down really quickly, well, you're going to get a large time derivative. And what your ring is going to do, it's going to get an induced current in it that's going to oppose the direction of that change. So if we have a current flowing this way, it's going to make its own magnetic field and that's going to combine with this external magnetic field. And it's going to kind of try, we're not really thinking about these things with minds of their own, but what its effect is boosting that magnetic flux back up in the direction that it used to be. Because that's the direction that you're getting your voltage, VEMF. We're doing this integral, and we're not really getting too much information about the vector value of this. We're taking this whole thing, and we're doing this dot product. We're counting up how much flux we're getting, and then we're taking the time derivative. So we need to do a little bit more math and look at how are we going to do this derivative, this whole thing right here. If we're sticking with the idea that we've got this external magnetic field, and that in the case where the limits of integration are not changing, assume limits of integration is a special case, as we saw last time, just talking about that thing where we're changing the area. It's not always the case. Assume limits of integration aren't changing. And in this example, that means the area of this ring here is staying constant. Then we can bring that ddt inside the integral side. B, and just apply it to the integrand, dt dot ds. It's still a vector, we're still going to do a dot product, and we've got a minus sign that we keep track of. And on the other side, we can, well, v is e dot dl over some path. And we're heading towards the magic of Stokes' theorem. If we've got a closed path, we can equate it to the curl of E. Curl of E dotted with ds over that same, and this surface is bounded by this path. That's the connection, Stokes' theorem. And like we're used to doing, well, what I ought to do is move this minus sign inside there. Why not? Because we're used to equating the integrands. When we work these things out and we start seeing, well, yeah, we've got the same structure. This is the surface. This is the path. It's the same surface, both sides of this thing. So the integrands have to be equal at each point in that integral. So we can take those integrands out, this and this. For it to work out every single time, it's got to be equal point by point. B dt. I'm doing what used to be Faraday's law in electrostatics gained another part. It used to be 0 right here. E dot dl used to be 0. No longer electrostatic. So the whole goal of chapter 9 is to make time-varying things happen. Now we've got a time-varying field, so Faraday's law still boils down to you got 0 on this side when you have a constant magnetic flux density. But now with changing B, we get to see finally the coupling between the electric and magnetic fields. We're going to do something similar with Ampere's law.